equivalent. That is by your S. This one's supposed to be your equivalent. So if yours is equivalent, you substitute your Z equal to your E power minus J. But if you
No, I think he never write just reflect.
But if you substitute this one in, this one, you substitute your EJ omega T in, this is how you get. And this one is your sine, it's your 2 sine, this one is your 2 cosine. So you use sine divided by cosine, you get your tangent function. So basically you come out on tangent function. And for this case, if your cutoff frequency is still A, you put your A substitute your omega, your 2 over T. This one will be your cutoff frequency. And remember what your cutoff frequency you need. In your original design, you want this one to be A. But is it this two to be the same? Is it this two to be the same? You can try to use your calculator. You put, let me see, your omega is 1 kilohertz. Let me see, your A is 1000. You put this one.
What do you get?
If let me see your sampling time.
Oh, I didn't do it. Oh, what didn't do it?
If let me see your sampling time is also 1000 hertz. What you get?
What's in the home, man? I agree.
Are you going to get 1000? You may not get 1000, right? And what if your sampling time is 1 megahertz? If you're 1 megahertz, what do you get? Then how much will be your cutoff frequency? Definitely it won't be the same as 1000. Right? So there's certain design issue because your sampling rate, because now your cutoff frequency, it depends on your sampling rate, it also depends on alpha. And actually this one will be only equivalent if your AT divided by 2 is very, very small. If you want this one to be the same as your A, basically you means your AT divided by 2 is equal to omega 1 divided by T divided omega 1 T divided by T. So basically what you want, if you want this one equal to A, what you want? You want your tangent AT divided by 2 is equal to your AT divided by 2. Through your math, you know this one will only be equal if the value in between is very small, right? If this one is very small, then they are equal, right? Otherwise they are not equal. So since they are not equal, so there are certain difference. So what should we do? So which means if you just apply the Hutchins method, you will be able to get a depth function, but you will not be able to achieve the design performance what we want. So what we need to do, we need to do a rebacking. So we need to do something to commonly back. So in the past 2 years, every year they come out question. First step ask you to come out the Hutchins method, and secondly ask you to do the rebacking. So how should we do the rebacking? Okay, the process. Okay, because some students told me you prefer to know just step by step, okay, how to do. So let's highlight the steps. And some of you prefer just remember. So this one is also something for you to remember. So for this one, we only got 3 steps. And please listen carefully. So what are the 3 steps? First of all, you should rewrite your transfer function instead of hs. You need to rewrite as your h as a function of s divided by your omega 1. So this, your omega 1 will be your critical frequency. So this one, later after the so-called the free wrapping, you will make sure at that critical frequency, you will obtain the same result, okay, as in your S function. So if your frequency is your A, if in this scenario your critical frequency is A, so previously your function Hs is equal to A divided by S plus A. So what you need to do? I need you to rewrite your function in a form of S divided by omega. Now your omega is A, so I need you to rewrite your S function as a function of S divided by A. But because these two must be the same, right? So this one you divide by A, you multiply it. So this is what we mean. Rewrite your practice transfer function with the variable S divided by your omega. After you have done, then you have to calculate what is the condition. Okay? For your A to be equivalent. In this case, you want your A to be two over T tangent function of your omega 1 T divided by 2. So just now you have your omega 1, so later you just substitute your omega 1 by this A. So this A will be no more than A. So in order to not confusing, so I put this one as omega. Because this one is a little bit tedious. If you read your textbook, you may find a little bit confusing. Because sometimes you mention about A, sometimes you have your omega 1. And actually you don't have your omega 1 previously, right? So this is the thing I purposely highlight like this way. So now you know your omega 1. How you obtain your omega 1? Is through this way to omega 1. And later you have your omega 1. Then you need to replace that omega with that A. And then finally you can substitute that S with your Z function. Okay, the last step is easier. You just substitute your S into your new function. So what's the difference? Where the free value come from? If you compare with the previous one you have your S function. Then you substitute your S as a Z function. This is your previous one. Previous one, you substitute your S into your HS function directly. But now instead of substituting to this HS, we are going to do some free mapping. We need to do something with your HS. So instead of HS, you have your S over omega. Okay, and where is omega come from? The omega comes from this A. And why we get this A? Why we have this one? It's because we understand in order for this to be the same, I want your A to be this. Because this is your cutoff, is your critical frequency. So this one can make sure after pre-mapping at that critical frequency you will obtain similar performance in your Z domain as in your S domain. Okay, but this one can only guarantee, okay, and also bear in mind, this one only guarantee at that frequency. It never say after your pre-mapping, your Z function could be exactly identical as your S function. It's only guaranteed that frequency. For example, in this case, the low pass filter, because the cutoff frequency is the most critical frequency we are looking at. We want at that cutoff frequency, my power is up. Because that one is a frequency to define your bandwidth. Because your bandwidth of your low pass filter is dependent on your cutoff frequency. So that cutoff frequency response is very important. Okay? Of course, we understand this one is too abstract. So the good exercise is to show the example. So for this example, we have exercise question about the textbook. So in this question, we have a freeze compensator. For this freeze compensator, after you have done your dynamics control and your design technology about the controller, you will notice if you design your edges like this, work this one. This one will give you a 60-degree freeze peak. And where your omega is 0. So this one is a freeze compensator. So if you design a freeze compensator, you want where your frequency at 3, you want this one to give you a 60-degree, okay, freeze peak. So we will skip the one forward backward, that one is going to the next slide after class, and next week we will show you the answer. We are going to look at the pre-mapping one. So for this one, if we substitute directly without the pre-mapping, so this is your substitution. Actually very simple, you just substitute this one in, right? I will urge you to do exercise. If you never try, you will never learn. Okay? So you substitute this one in, you get your Z function. And you just do a simplification, you get the Z function like this. After you have the Z function, if you want to do the freeze analysis, you will notice this one is about 45 degrees. Okay, it's about 45 degrees, not 60 degrees. So what is the percent of the degree mapping? You see the bilinear rule of the custom rule is very simple. Just substitute this one in. So for the free mapping one is slightly more complicated. So first of all, this is your HS. So what you need to do, you need to pre-mapping this one. So instead of S, you need to rewrite this one as a S over your critical omega. Now your omega is 3. So you need to write this one to be S divided by 3. But this one is not just change your S to S divided by 3. So your HS is equal to your S plus 1 divided by 0.1 S plus 1, right? So what I mean is, I want you to rewrite your S function as your HS divided by omega, which is your S over 3. So how can you get your S over 3? But your HS still be the same function. Is this still plus 1? No more plus 1, right? Because this one you divide by 3, this one you also need to divide by 3. To make sure these two are equivalent. Your transfer function at this step, they must be equivalent. Are they equivalent now? Are they equivalent? They are equivalent, right? Are they equivalent? They are equivalent. After you get this, still remember what you have done in your math about function. In this function, what is your variable? Is it your variable is still s? No. Now your function is a variable of s over 3. So the first step, your s function, the function is the same. But you just rewrite your function instead of variable of s. You write your function as a variable of s over omega. In this scenario, it's s over by 3. So the function is still the same. You rewrite your variable from s to s over 3. Is it clear? So after this, now we are going to do a mapping. Because this 3 will be mapped as A. So this one, instead of 3, I put 8. Please notice the shape here. From here to here, the two functions are identical. Alright? These two are identical. Later, I do a mapping. I have replaced your omega 1 by 8. And later I'm going to do something. What I'm going to do? Because my A is no more 3. This is something please be careful. My A will be 2 over T tangent omega T by 2. So now you know your frequency T, you know the sampling time T, you know your critical frequency omega is 3. So after you put in, you get the value. So now, from here to here, actually they are not the same, are free mapping. So this is where the free map comes from. From this step to this step, these two functions they are identical. Right? This one, they are the same. From here to here, they are not the same. I have do some tricky part. I replace your omega by k. And where your a is equal to so in this case, after I calculate, this one is 3.149. Then I'm going to substitute the a by 3.149. That's what I get. So from here to here, from here to the original one is something called the free mapping web. Can you see the difference from here to here? This one and this one, are they the same equation? No. This is so-called the free mapping imbalance. This is the most critical part. After you have done this, then it's simple. You just substitute your S by the Castings method. So then you just substitute your 2 over D, Z minus 1 divided by Z plus 1 by your S. Then you find your S to your Z. So the most tricky part is this part, from here to here. This one you rewrite this one in the form. It's a little easier. Because later you just want to substitute this value, you're going to get this value. You are going to rewrite this value by your new A. Instead of omega, you are using your A. After you obtain this, then the rest is the same. You just substitute your z function to substitute your s. After you get this, this is the function you get. And this is your linear function with prime value. And after class, I urge all of you to do all the exercise. We have 2 exercises from the textbook. Okay, we have 2 exercises from the textbook. This one is the one, okay, we have shown as an example during the class. Okay? And we will go through the detail about this one, okay, next week. But we need you to do exercise first. I really don't want the students just be a photocopy in my class. I show you answer in copy done. Then you try to do it. Then after exam, yes. Okay, you have to do first. Then you may have certain doubt. Okay, then we go through the question. And we also show you the last 2 years exam. Okay? So in 2004, which is last year, they give you a low pass filter and ask you to find out the equivalent by the casting method, then do the pre-mapping. 2 years ago, ask you to derive a different situation of this one using the trapezoidal again. Then design a discrete, okay, equivalent. So if you look at the exam concern resulting report, I do hope you have a good motivation, okay, to do this exercise. Okay? And we are going to discuss, okay, how to solve it next week. But before I discuss the solution, I want you to do the exercise. Okay? And this one you must do before next week. Alright? Okay, so that's all for today.